So we've got the sequence. We've got the first four terms that we wrote out, the explicit integer terms here, not just the recursive formula. So then here's the question that we actually care about with respect to induction. We want to show by induction that this particular sequence is closed formula. So that's the explicit formula. The formula that looks like a function is this guy. So nth term equals 4 to the n plus 2 times negative 1 to the n, and we want this to work for all values of n. We want this thing to work for the first two terms that were just given to us. We also want this to work for all of these terms that use the recursive formula. Okay? So that's what we want to try to prove. All of this stuff up top, all of this stuff before this line, that's given. We know for sure this stuff occurs. This formula right here, that's the closed formula, that's the one that we're trying to figure out. Okay? So in order to go ahead and do this, oh no, don't freeze on me. All right. In order to go ahead and do that, first thing is basis step, and we did this last time. Let me actually shrink this up a little bit so you can see where the numbers are coming from. We said, all right, well, if n equals 0, that's the first term is 3, and then if we plug into this formula, we'll also get 3. N equals 1, well, that was also given. It was going to be 2. And if we plug into this formula with n equals 1, that also equaled 2. And then when n equals 2, that's the first time we use the recursive formula right up here, and we needed to use the recursive formula. That's the main one we're using. We said, hey, we already found that the term was 18. If you hadn't found the term previously, if we hadn't done this step previously, this is where you'd actually plug everything into your recursive formula and have to find the 18 right here. Okay. Then, same as before, we'll plug in n equals 2 into the formula that we're hoping works, and we found 18 as also the answer. So in the basis step holds just fine. From checking a couple of test cases, this formula looks reasonable and believable. Now, then we're ready to go ahead and look at the hypothesis step. Don't overthink it. The hypothesis step is almost the same as before. We're going to assume this works when n equals k. But now, here's a new thing. It's also supposed to work for every value of n smaller than k. So we are going to assume, and let me make sure I'm actually having a drawing implement. So we will go ahead and assume that, and I'll go ahead and list them down in a row, just in a column, just because that's easier for most people to see, that when n equals k, so the kth term equals 4 raised to the k plus 2 times negative 1 raised to the k. And we're going to assume that all the previous terms have the same formula. So when n equals k minus 1, replace all the n's with k minus 1. So we'll have a subscript k minus 1 equals 4 raised to the k minus 1 plus 2 times negative 1 to the k minus 1. I'll do one more and then do dot, dot, dots. 1 less than k minus 1 is k minus 2. So over here to the side, this is when n equals k equals k minus 1, n equals k minus 2, and I'll stop at that last one. So this guy would be 4 raised to the k minus 2. Notice I'm just replacing the n in the boxed formula up at the top there with k minus 2. And let me go ahead and hide this so we can see more of it. Okay. Then dot, dot, dot. And this is supposed to work all the way down to our basis steps. In other words, n equals 0. So this is 4 raised to 0 plus 2 times negative 1 raised to 0. And that's one that we already know. So that's how the hypothesis step changes in strong induction. Now, when we get to the actual induction step, I'll show you how you determine whether you've got strong induction or weak induction. So then we have our induction step. And in our induction step, we want to prove this boxed formula right here. Now, with sequences, you always start on the side that's the name of the sequence term. So you start here with an. So consider, or as we said last week, then an equals something. Now here's what we don't know. Oops, we don't want n there. We want n to equal k plus 1. So let's go back and erase the n and replace it with the k plus 1. All right. So here's what we don't know. We don't know if that boxed formula at the top, the one that says our terms equal 4 to some power plus 2 times negative 1 to some power, We don't know for sure that that works when n equals k plus 1 because that's what we're trying to prove. So let's do a little scratch work over here to the side. I'm going to go ahead and put it in a different color just so we know it's scratch work. So here's what we're looking for. When we're looking for this statement when n equals k plus 1, we need the n on the a subscript n to be k plus 1. Well, we already wrote that down, so we're good there. And on the other side, I'm going to go up and just copy this part here. So on the other side, we have 4 raised to the k plus 1, or at least that's what we want to have happen, plus 2 times negative 1 raised to the k plus 1. Okay? So this guy here is where we're going to start. With sequences, you always start there. And this side over here is where we need to end. Please note the second step can't be that guy. That'll be the very, very last thing we're going to write. Now, what do we know? Okay. Well, in terms of what we do know, this is where you go back to the top and say, all right, well, what were we given? Well, we were given, let me wiggle my cursor here so you can see what I'm looking at. We were given the first 2 terms, not helpful right now, in n equals k plus 1. And we were also given this recursive formula. So this recursive formula right here, and then those top 2, this is the stuff we're given. This is what we know for sure about the sequence. So if we have n equals k plus 1, we can totally rewrite this formula with respect to our n. Okay? So let's do that next, and let me get back to where I can write something. And I'll go ahead and put that scratch work over here to the side too. Specifically, we had an is supposed to be 3 times the previous term plus 4 times the term before that. Make sure I copy that guy down correctly. Yeah, all right. So when n equals k plus 1, you guys tell me, what should I write after the 3? In other words, what's the subscript on this term after the 3? What do you guys think? If n equals k plus 1, what would n minus 1 equal? Yep, perfect. Anybody got what should be the subscript on that next term, the one that's after the 4? That's where we're supposed to have n minus 2, and n is supposed to be k plus 1. Yep, so that one would be k minus 1. Notice what happened. Whatever subscript we started on, if we follow this pattern, 1 less is k, 1 less still is k minus 1. Okay. So what does that tell us? That tells us this is a format, this recursive formula we know for sure works for all terms in this sequence. So that means we can rewrite our current k plus first term as the 3 times the previous term plus 4 times the term before that. So I'm just going to copy what we just found. So this is 3a to the k plus 4a to the k minus 1. Now remember what we're trying to get to. We're trying to get to 4 raised to some exponent plus 2 times negative 1 raised to some exponent. Is there any way that we can convert these a subscript k and a subscript k minus 1 into something of exponents with 4s and negative 1s? Anybody have a guess what we should do after this next equals? If you want to type in the formulas, you can, or you can just give a description of what we should use. Anybody got a guess where to go next? And then there's just lots of silence. All right, so think back to regular old induction. What would we have done at this step if it was regular old induction? No guesses? Okay, well hopefully you were all thinking in your head, when we write something out, oh, here came something. Ooh, unfortunately, no, but that is a really good guess. So that is something that's actually often something that somebody would show you in like a high school math class, where you would set what you have equal to what you're hoping to get to, and then you do all of the algebra on both. I need to show with my hands. Just a second here. All right. Hi, guys. All right, I'm attempting to get this, so I'm looking at you guys. So that would be like you have two things, and they're set side by side, and then you're showing what's going on both sides, all the algebra, until you get to the bottom, and they're all equal. And that's a perfectly fine way of first doing it, but that's not a proper math explaining why something works, okay? So that totally is a way of doing it, but that only make that scratch work, okay? So in terms of proper math, you have a start, and you have an end, and you need to go directly from the top where you started to the bottom where you ended, okay? But yeah, what you were talking about is totally something that you see in, I mean, I remember doing that in high school math classes too, but as soon as, when we get to college, we transition ourselves up to proper math, whatevers. It's sort of they don't tell you that's not quite correct, but it's slightly circular logic. It's like you're assuming what you want to have, even though they normally ask you to do little question marks above the equals. But yeah, that's in the back of our heads. That's totally what we're going to be thinking. Okay, it's one of the reasons. That's also one of the reasons people often say work top down and bottom up, sort of like going towards the center. That's that same idea. And again, totally fine in scratch work. But once you write it up formally, or once you write it up for a submission, it needs to be slightly different. So let me show you how you would transition that. I'm going to go ahead and hide this. That way when I start writing on my stylus, you don't like look up my nose and stuff like that. Because as much fun as that's not, we're just not going to do it today. All right. So what we want to do is get to this same end. We totally want to do algebra to get there. And again, if you want to do that sort of two-column thing, in terms of your scratch work, do it. It's definitely a good way of first starting, but then, I'll just do it here. Here's what I often see. Doop, doop. Do all your stuff, and finally that you get to both sides, they actually do equal each other. Here's how you undo it. And if you guys were all writing this stuff by hand, you would totally get notes like this. Write that part, then switch over to this part, and then go up. That's how you translate them. Okay? But definitely great in terms of how you think. And I am obviously need more coffee this morning because I'm repeating myself. All right. So did everybody get the picture if they wanted the picture, because I'm about to delete it because I put it on top of where we need to write. All right. I'm seeing nobody shout out with a no. I will wait about a couple seconds. All right. So I'm going to go ahead and delete this. So let's see what we would do. What we want to do is all the algebra to get us to the other side. So remember, you always need to use your hypothesis step. So let's use this first one. Anybody have a guess why I might highlight that? Because we want to do what with it? So these are the things we assumed. So we're going to go ahead and plug it in. Now notice, this formula only works with the term AK. So we'll have 3, no worries there. And we can write in the thing we just highlighted. So there's the 4 to the K. And then we'll have the 2 times -1 to the K. And then we'll have 4 times something. Anybody have a guess what we should put in this something? Remember, we're plugging in from the line above. So what could we plug in for this A with a subscript K minus 1? Anybody have a guess? Don't overthink it. And with the silence, that either means you're overthinking it, have no clue what's going on, or are typing. It's always difficult to know which one it is. Awesome, typing. And it is okay if you tell me you have no clue what's going on. Please let me know when that happens, okay? All right, so yes, what do we want to do? We want to pull the formula for A with a subscript k minus 1. So we want to pull this guy right under the highlighted version. So that's the exact same thing that we just did. Notice this is where strong induction occurs. It's where you use your hypothesis step more than once. That's what makes it quote-unquote strong induction, because you're using your hypothesis step more than once. So I'm just going to straight up copy down what A with a subscript k minus 1 is supposed to equal. And so this is the 4 raised to the k minus 1. Let me go ahead and highlight this for you guys so you can easily see where I'm grabbing from. So it's the highlighted in blue guy. And then plus 2 times negative 1 raised to the k minus 1. Now, good news. At this point, remember what we're still trying to get to. We're still trying to get to this 4 raised to the k plus 1 plus 2 times negative 1 raised to the k plus 1. So we're now we now have powers of 4 and powers of negative 1. Awesome. You mean this 3 right here? Alright, so this formula right here, and let me underline this one in orange just because we have so many formulas right now. That whole formula, the 3 as well as the 4, actually came from the original given piece of information. So we were told that for every term in the sequence, you knew that expression, that the term equaled 3 times previous term plus 4 times the term before. So that's where it came from. Yeah, no, watch out. The ones with sequences, by far, once you get into them, and we'll have another, depending on time, I'm hoping for 2 more examples. The sequence ones, they definitely have a pattern, but there's a lot of stuff going on. So we throw in the recursive formula that we're told we know for sure. Then we replace the 2 previous terms with what we saw from the hypothesis, from the assumption step right here. Everything else is just going to be some algebra where we try to group all of the powers of 4 together and all of the powers of negative 1 together. Why would we have that strategy? Because we're trying to get to a power of 4 plus a power of negative 1. So let's do it. So here's what we've got. We've got, and I'm just going to go ahead and grab the powers of 4s first. So we've got 3 times 4 raised to the kth power. And we've got another power of 4, so this is plus 4 times 4 to the k minus first power. So those 2 are now grouped together. Now for the second term, watch out, don't forget the 3 gets distributed in. So this would be what? That looks like 6 times negative 1 to the k. And then for this guy over here, we'll multiply the 4 in, so that looks like an 8 times negative 1 to the k. Do a quick double check. Make sure I did that multiplication correctly. Oh, but I did do a mistake. Anybody spot the mistake? It's in the second set of brackets. Anybody spot the issue? Ooh, that part, no. So the 6 right here came from the 3 times the 2 from the first term. So I split it. So this part here went there, that part went there, this one with the 4 went over here, and this 2 went down there. Yep, there's the issue. I forgot the negative 1. It's subtle, but it'll totally change your answer. Okay. So in this particular case, what do? We'd love to be able to combine these into a single term inside of both brackets. Why? Because the thing we're supposed to have is only 1 power of 4, only 1 power of -1. So let's do the first one. And for the first one, notice we've got this 4 times a 4 raised to the exponent. This can totally be simplified into one exponent. Anybody got a line on which exponent that is? What the new exponent would be, I should say. Yep, just a plain OK. Now notice what happens. Now that you've got a 4 to the k on both of these, there's 1 4 to the k here and 3 4 to the k's there, which means all total we have 4 4 to the k's. But what is 4 4 to the k's? That's 4 to what exponent? What's the new exponent? You got it, k plus 1, perfect. Not going to lie, that's the easier side, although we're going to do almost the exact same thing with the -1s. Okay? So thinking about that, how we wanted to put everything compiled together if possible, and then add them together if possible to do the same thing over here. There's one little bitty difference. Okay? And these guys, notice again, we're going to want to get the -1 raised to what power? We want to get it raised to a power of k plus 1. Okay? So you guys see if this looks believable. I am going to claim the following. I am going to claim that if we rewrite that as -6 and then -1 raised to the k plus 1, that is exactly the same as the original +6 times -1 to the k. We'll put the work to the side of what trick I used. As with -1s, there's actually a trick you can always use. Ah, good question. It doesn't. So here's where things went. That guy went there. This guy went there. I regrouped. Do the arrows help? Oh, good. Okay. Because it looked like a couple of you were seeing that same issue. Yeah. So what I did here is in the original one, after the plugin step, I just regrouped, and I regrouped so we could pull all. It's the same thing of combining like terms. That's all that was happening is I grouped the terms that were similar together in the hope that we could combine them. All right, and so we dealt with all the ones that had powers of 4, so now we're dealing with the ones that have powers of -1s. So let us look at the trick, and I think I'm still on orange writing, so let us get out of orange writing. I am going to claim the following. I'm going to claim that -1 squared equals something. Anybody remember what -1 squared equals? Don't overthink it. Yeah, -1 squared equals 1. Now, why would I say that's the trick that I used right here? Well, it's because I flipped the sign on the 6, right? Positive to negative. And I actually included one extra copy of a -1 inside the power. So I essentially multiplied both of these guys by -1. Well, if you multiply two terms by -1, that's just a really, really fancy way of multiplying by +1, which doesn't change your term. And that's the key thing right there. Okay? So this is just a really, really fancy trick. It only works if you have -1s raised to powers. I guess technically you could use it for other guys too, but it only legitimately helps normally when you've got the -1s raised to powers. Now notice here, that gets us bumped up to the exponent of k plus 1, which is the total reason of doing it. Multiply this guy by one extra copy of -1 to bump it up to the exponent we wanted. We said then, oh, you multiply by a -1, that changes your answer, so we multiply the outside by a -1 as well. Or you flip the sign back to what it should be is the other way to think about it. Now over here, notice what happens. This one let me do it in legitimately 2 steps. We have 8 times -1 to the k minus 1 How many negative 1s would we need to multiply this guy by to get an exponent on the negative 1 as a k plus 1? Anybody have a guess of what exponent I should put on this second term right here? Remember, we want the new exponent to be k plus 1. You currently have k minus 1. How many more factors of negative 1 do we need? Here's another way to think about it if it helps. Remember, exponents get added. So we need to figure out what that question mark is. Anybody have a guess on what that question mark is? Because that question mark is the exponent we'll put on that little copy, that extra factor of negative 1 at the very end up there on the term with the 8. This guy. Nope. I was looking to see if you guys had any guesses. And then my cursor went wild. What do you guys think? What should go right here in that question mark? Hint, it will be an integer. Yep, that would totally be a 2. Why? Because if you add 2 to k minus 1, the minus 1 and the 2 will combine to get you a positive 1 right there. So our exponent up here is a 2. Now, what do we know what happens here? Well, negative 1 squared is 1. So if I multiply this negative 1 squared at the end, that doesn't change the term at all. I mean, yeah, it changed what it looks like, but it doesn't actually change the numerical value of the term whatsoever. So everything else stays exactly the same. Okay? Everybody okay so far with that? I realize it looks crazy and wild and possibly ridiculous, but do you believe that it's true after somebody else did it? And if we didn't have a negative 1 here, it actually would be just as easy as when there was the 4s. All right, seeing nobody yell yet, let's move forward. So notice what we have right here. We now have negative 1 raised to the k plus 1 in both of these two spots. So that means we're going to be able to combine like terms. Here we have negative 6 of them, and here we have positive 8 of them. So then what happens? You add them together, and you'll have the same negative 1 raised to the k plus 1. And if you've got the negative 6 and the positive 8, when those combined, you'll get the positive 2 out front. Okay? Now go ahead and move this scratch work over to the side and box it. That way you can still have it if you want to look at it, but it's not right in the middle of the problem. And that is exactly what we were trying to get to in our n equals k plus 1 step. So I'm going to make a check mark and say, yes, we're good. It works. Okay. So notice, just like with our other guys, what happens? You've got a starting point, you've got an ending point, and there's often just a bunch of algebra to remember and play around with here. Now, what a lot of people like to do is they'll start from the top and they'll start to the bottom. That is totally mimicking that thing we talked way too much about earlier today of if you had 2 columns. Okay? And then you try to make the 2 pieces and parts meet in the middle. But logically speaking, make sure you start at on one side, end on the other side, and make sure all the middle steps are in the middle. Okay? Now, conclusion. Since it worked out, our conclusion here would be, thus, this formula works for this sequence. And I was too lazy to write down the actual formula. Okay? Questions make sense? Kind of feeling a little bit okay. Could at least follow it when I did it, which I think is where we're at right now. All right, well, let us look at another example. So suppose we have this next example. Again, it's going to be an example with a sequence. So our example is, and I'll go ahead and write this as a BN, so like second sequence. And this one here is a little bit more straightforward. So this sequence says previous term plus 2 times the term before that. So still the same subscript n minus 1, n minus 2. Here our first 2 terms are b1 equals 1 and b2 equals 3. Although we've been doing zeros and ones, so we might as well switch that to 0 and 1. We've been doing that for all the other ones. Doesn't really matter, you just have to pick what we're going to start with. So we can start it, n equals 0. Okay. Ooh, no, I do need to make sure that I start at the right subscripts. Let me undo what I just did. Because this one is going to be more picky about the subscripts. Then what do we want to do? We're going, and I'm on purpose going to leave a space so we can write out some of the terms of this sequence. We would like to use induction to show that if we look at any term in this sequence, it is always less than or equal to 5/2 raised to the nth power. And this is true for all of our terms. Okay. So first thing is, let's go ahead and write out a couple terms of this sequence. The very first 2 terms are simply going to be 1 and 3. They're given, you don't have to think about it. And then for the next, let's say next 2 terms, it's going to be dealing with what? Well, this one here would be n equals 3, because we started at n equals 1, n equals 2, n equals 3. So this would be the previous term, which is b2, plus 2 times the term before that, which would be b1. So this is 3 plus 2 times 1, or 5. And then if we do the next term, let's do the next term over here to the side so there's more room. So b4 would be b3 plus 2 times b2. We know what both of those values are now. b3 we just found was 5, and b2 was given to be 3. So what is that, 11? 5 plus 6, yeah, that should be 11. And then the sequence keeps going, but let's stop there because I'm lazy. Okay. So that gives you an idea of what the sequence looks like. Now, what does this tell you? It tells you if you look at each of these terms, it doesn't say they have to be a power of 5/2. It just says they're going to be smaller than some power of 5/2. Now, if we want to use induction, the first thing that we would do is, I'm going to go ahead and title this since it wasn't in the directions. The first thing we would do is use the basis step. Now, when we look at our basis step, you always look at your smallest values of n. So for us, we have n equals 1 is the smallest value of n. Here, we've got b1 equals 1. And if we looked at 5/2, plug in 1, well, 5/2 is what? That's 2.5. Is 2.5 larger than 1? What do you guys think? You guys tell me. Is 2.5 larger than or equal to 1? If the answer is no, we stop right here and say, nope, this doesn't work. Yeah, so this works. It's totally larger than. We're good to go. So then we look at, all right, well, n equals 2, because notice n equals 2, this guy was also given to us this second term. So b2 is 3. So if we check, hey, do we actually get when 5/2 squared, is that bigger than 3? And this is where you actually have to calculate 5/2 squared. So this is what? This is 25/4. So 24 is 6 times 4, so this would be 6.25. Or put it in decimal, which is perfectly fine too. So what do you think? 6 and a little bit, is that bigger than 3? In other words, does this n value work with the inequality? What do you guys think? Are we still doing good? Or was this a case where everything failed and we get to stop? Is 6 bigger than 3? That's really the question. I'm going to assume you're all thinking in your heads yes. So this one also works. Then we'll have n equals 3, and n equals 3 is the first time where we actually had to use the recursive formula. This is where we calculated the 5. So we'll pull the calculation of the 5 from previously, but this is where we actually used our recursive formula. Okay. So if we then look at 5 over 2 cubed, well, this is 125 over 8. Oh my. Well, if we tried to figure out what that one was, we'd say that 8 goes into 12 once, 4 left over, then we have 4 and a 5. 8 goes into there, what is that, 5 times, and then there's 5 left over. So that would be 15 and 5/8. This still looks like it works just fine, that is much larger. So I'm going to go ahead and say, yep, we're still good here, and in fact, it looks like it's not close. It looks like it's quite a bit larger than our sequence terms each time. Okay. This here, once you've gotten the 2 individual initial terms, and then you grab the main formula that's defining this sequence, you're done with the basis. So notice, just like before, we had 1, 2, 3 n values we had to check for our basis step. Once you have your basis step, you're ready for your hypothesis. Now let's suppose that we can actually just use regular old induction here. So if we use regular old induction, what would we say? The hypothesis statement would say, assume that everything works for n equals k. So this would be assume that bk, so here, what's the formula we're looking at? We're looking at this inequality. So this would be assume that bk is less than or equal to 5 over 2 raised to the kth power. Okay. And this is some k that's appropriate k. It's got to be bigger than 1. I guess technically you could assume it's 1, but you're really looking at bigger than 1. Okay. I'm going to on purpose leave a little space there because if this guy turns into strong induction, we'll add in the extra things we need. So this example, even more than the last one, very much illustrates when you would be using your induction, okay? Or when you decide which type of induction to use. So this is now when we look at n equals k plus 1. I would always recommend over to the side, do a little bit of scratch work. We used green last time and it didn't really show up. Maybe blue will show up better. So here's what we need when we're looking at our n equals k plus a first statement. We're looking to see if that boxed formula works. So I'm going to change out the n's in the boxed formula up here at the top to k plus 1. So we'll have the sequence b subscript k plus 1 less than or equal to 5 over 2k plus 1. Don't overthink it. Notice I just switched out the n's with the k plus 1. Since we're dealing with a sequence, you always start with the sequence term. Otherwise, it gets really hairy really fast. And you always end with whatever's on the other side of the inequality or the equal symbol. Okay? Everybody comfortable so far? All right. So what would we do next? Well, then we look at, did not mean for that to be blue. So then we look at, well, the starting point, and our starting point was b subscript k plus 1. Now here's what we know for sure about this guy. We know for sure we have this recurrence relation, this recursive formula that says bn equaled bn minus 1 plus 2bn minus 2. And this is 100% just the formula from above that I just copied down. So if n equals k plus 1, what do we know about this guy? Well, we know that if n equals k plus 1, we'll get b, and what subscript should these two b's have? The first one should have what subscript? You guys tell me. Anybody? Remember here, n equals k plus 1, copying to the formula right here. Yep, formula right here. If you subtract 1, would be k for the first one. And for the second one, when you subtract 2, it would be k minus 1. So we're just going to go ahead and copy that down. This is something that was given to us. Granted, we had to adjust it for our specific value of n, but this formula was the sequence that we were originally given. So don't overthink it. This is not something you have to prove. This is something that you know for sure with a sequence. Now, once you're at this stage, what do you guys think we should do next? So what do we always do in the induction step? We always need to plug something in. What's the thing that we always plug in some way, shape, or form? If you want to type out the actual symbols, that's totally fine, but all I'm looking for is a description. It's perfectly fine too. What's the thing we always plug in? In other words, when you get into induction, this is probably one of the most important things to know about mathematical induction. Strong version, weak version, whichever version of induction you're using, when you're in the actual induction step like we are right now, there's something you always have to do, otherwise you're not doing induction. It's all about who you plug in. Who do we plug in? What do you guys think? So yes, this question is out to you guys. Anybody have an idea? If you're not sure, this is the point where you need to grab like a piece of paper or something and write it down. Almost the word you used is off, but the right idea, we're always going to plug in from the hypothesis. So the thing that you assumed right here, whatever you assumed, you have to make sure that you plug it in somewhere. So when you get stuck, this is where you say, all right, well, I knew this from the fact that we just had this particular sequence, and then you're like, well, I'm stuck. I have no idea where to go here. This is where you say in your head, oh, let me go back to the hypothesis and let me plug in. So for example, this first term right here, we're going to replace the b with who? Well, this 5 over 2 raised to the k, and since that was an inequality up there, I needed to switch that equals that I originally wrote to an inequality. Now, that being said, we plugged in for bk. What should we do for the term that's b with a subscript k minus 1? Anybody got a guess? I know this one will take a little bit longer to type. But anybody have a guess of what we want to plug in for after the 2, for that second term on the left, on the right-hand side of the equation? What do we want to do here? I'll wiggle my cursor so it's easier to see. In other words, what do we replace this b with a subscript k minus 1 with? Oh, please don't replace it with 0. Please don't. So I'm going to claim it should be 5 over 2 raised to something. Anybody have a guess what the exponent should be on the 5 over 2? Don't overthink it. Might be helpful if I do this. You can see everything we had previously. Yeah. So what we want to replace the b subscript k minus 1 with, so that k minus first term with is the 5 over 2 raised to k minus 1. Please note, when you replace two things right here, two replacements right there, that's when you know what? In the hypothesis step, we actually needed not just this guy that we wrote down, but we also needed it when n was k minus 1, so we needed this assumption too. And that's what converts this into strong induction, was the fact that we needed that second one. And then it keeps going all the way down until you get to the into the basis step. Okay? So that would be how to tell that you're dealing with strong induction as opposed to weak induction. And notice if you want a little note to yourself, you could over to the side, instead of saying n equals k, say n is less than or equal to k would be a way to indicate that you need all of these. Okay? So that would be how you tell that you need induction. Now the rest of this is just going to be some algebra so that we get all the way to the n value that we want over here. So since we're really tight on time, I'm going to go ahead and just show you one of the ways that you can do it. Okay? So people do it in several different ways. Here's one of the ways. Notice how both of these two guys have 5/2 raised to a power. Take the smaller of the two powers. So I'm going to factor out a 5/2 raised to the k minus 1, k minus 1 being the smaller of the two exponents. So that's the smaller power. Now when we factor this guy out of the first one, there's an extra copy of 5/2. But when we factor that expression out of the second term, there is no extra expression. It's just plus 2. Okay. Now, I'm going to go ahead and add this together, and if we had a little more time, I might add it together in a fraction. I'm just going to give you what that sum actually equals. So this is 5/2, k minus 1, and if you add those together, it's going to be over 2. It turns out to be 9/2. Okay. Now, I'm going to, on purpose now, start at the bottom and work up to show you that other strategy, so make sure I have enough space. So what did we want? We wanted to get to 5/2 raised to the k plus 1. Okay? Now, what do we currently have? We have 5/2 raised to the k minus 1. So I'm going to split the answer that we want to get to and write it as 5/2 raised to the k minus 1, 5/2 to the, well, some exponent. What exponent should I put on right here? So here I change it to equals because we didn't do anything with the less than at all. We just did some algebra, made these guys exactly equal. The less than here symbol was because of the hypothesis step, because of that plugin. But once, it's not moving. But once you're not doing any changes, these next ones would be equals. Now, we're actually going to get another less than symbol, and the next less than symbol is going to turn in right here, which is why I've left this step blank at the current moment. Okay. So here, went ahead and said, hey, I can split this. I can take 2 copies of the 5/2 off, and I'll get this same k minus 1 that I have up here. Now, I need to compare this 9/2 with the 5/2 quantity squared. Well, 5/2 quantity squared is exactly the same thing as what? Same thing as 25/4. And this is where you have to do a comparison. You look at those two guys and you say, all right, well, which one's bigger, which one's smaller? And one of the things that I normally do is I normally just say, hey, let me get a common denominator because it's easier to tell. So if we change this 9/2 into something over 4, multiply top and bottom by 2, or you just plug it into a calculator and look at the decimals. So this one here is the same as 18/4, then 25/4, and then you say, all right, well, that means I have an inequality. The 25/4 is bigger. Now, here's the deal. Why do we care about the inequality symbol? Because the inequality symbols, it's totally fine to have equals, but your inequalities all have to go the same way. So if this inequality flipped the other way, that would be how this induction step fails. Okay. Now, where did we get to? We got exactly to the end that we wanted right over here, which means that this induction step works, and the conclusion here would be that, hey, yes, that inequality would work just fine. If you wanted to keep the inequality the entire time, that would also be totally okay. Just make sure you have the inequality that includes the equals in it, and then that would be just fine. The only time the inequality, keeping the inequality the whole time would be false is if you use the inequality symbol that did not include the equals. Okay? But yeah, that's totally fine to keep the inequality the whole time too. Okay? But that's it. The only thing left you do is the conclusion, and I'll go ahead and write in the conclusion right here, but this is it. We're done. So conclusion is that yes, for this sequence, we totally get that each term is less than or equal to, actually quite a bit less than 5/2 quantity raised to the same exponent as whatever the subscript was on the sequence term. Okay? But that's it for induction. I I don't have any extra good induction examples for you guys. So after the test on Tuesday, I don't plan to come back to induction unless you guys really want to. And remember, what we did today, which was strong induction, will not be on the test. On the test will only be the weak induction that we covered last week. Okay? So that's it. I don't have anything else for you guys. I'll hang out if you guys have any questions, but we are done otherwise.